Okay, so do you hear me well, first of all?
Yes, I can hear you.
Yeah, so as Ethan told, I'm going to talk about the problem of optimization. And this is a very important and core problem in many fields. Yes, in math and biology and of course computer science, machine learning. It appears like everywhere. Many problems can be formulated in terms of optimization problem. And we are going to talk today about some of the most general forms of optimization. And this is so-called unconstrained optimization. So what is this problem? So assume we are given some function f that maps d-dimensional vectors into real numbers, let's say. Okay, so we have such a function, and now we want to find some point x, d-dimensional point, such that the value of f at this point is the minimum one. Yeah, the smallest value of f at the point. So we want to find such a point. So of course, so why it is unconstrained? Because we don't have any constraint on axis or we are looking for. Yeah, it can be any x in d-dimensional space. Of course, many problems are formulated as constrained optimization. Yes, in many situations, in real situations, we have many constraints on the x we are looking for. But let's say we are talking now for the simplicity about unconstrained problem. And so there are many questions how to solve this. And even the question, the most basic question is, even such x, does it exist? And is there a point such that f attains its minimum? And if so, maybe there are many such points, not only one. So how can we find it? So if it exists, how can we find it? And how can we find it efficiently? So all these questions are being asked in this field of optimization, a huge field in math. And as Ethan told, we are going to talk and take this to the direction of machine learning. So how is this problem related to machine learning? So, okay, many problems are formulated even in machine learning as optimization problem. But if we think about deep learning, about neural nets, so optimization problem appears in the following scenario. So neural net models a loss of some problem. Yes, and what we are doing, we are trying to minimize a loss of representation of the model to the solution we are looking for. Yes, so in this sense, we obtain an optimization problem. We have a function which is a neural net, and we want to optimize its loss. So we have some function derived out of this model, and we need to optimize it. And there are many algorithms that can solve this problem. And in the case of deep learning neural nets, there is a very efficient algorithm that finds not the minimum. It's not guaranteed that the algorithm will find the minimum, but we hope in many scenarios that it will find the point close to minimum, and it will do it efficiently. And this algorithm is known as backpropagation, and I will talk about it later, not today. Okay, so this is the relation to deep learning, and now let's focus on a mathematical problem. Given some function from d dimensions that maps d-dimensional vectors to real numbers, we want to find some x in d dimensions that brings the function to the minimum value. So it's clear that we can't solve this problem if we don't make assumptions on the function. We need to make an assumption that guarantee that there is such a minimum. Okay. So the algorithm I'm going to talk is a gradient descent. It's a very basic algorithm, and there are many variations of it. And the guarantees of this gradient descent. So this gradient descent algorithm, it has theoretical guarantees. Once the function f satisfies certain properties, the algorithm guarantees that we will find this minimum point, and we will find it efficiently. And there is an exact mathematical formulation of the how many steps we need to. So this is an iterative algorithm, and it gives us the formula that says how many steps we need to do in order to reach this minimum point. So in a sense, this is a very a basic and very important algorithm in all this thread of optimization problems, because it has guarantees, while most of the algorithms in optimization do not have guarantees. Yes, we hope that they find a point which is close to minimum, but we cannot be sure. And here we can get these guarantees because we make many assumptions on the function f, which do not necessarily hold in real world situation. In most cases, they do not hold. But here, just to get a sense of these algorithms, we assume all these assumptions. So the idea of the algorithm, it's, as I told, it's an iterative algorithm. So the idea is very simple. So assume we start at some point. So we have all the space we want, right? We are not constrained by the sorting space. So we start from some point x0, let's say. I don't know how we chose it. Maybe arbitrary, maybe some smart guess, or maybe a randomly chosen point. So let's start from some point. And let's compute, okay, what is the value of f at x0? So we have some number, it's some value. So what would we want to do? Ideally, we want to go to the next point, x1, such that it will be guaranteed that if I measure the value of the function at x1, so the value will be reduced, right? Because we want to get smaller and smaller and smaller value. We are looking for the point x such that gives us the smallest possible value of f at this point. So if we can do steps, at each step we reduce the value of the function. So it is a good, so we can hope that after many steps, we arrive at the point where we cannot go to any direction such that this direction decreases the value. So we kind of converge to something. And we want to hope that we converge to the minimum point because we don't have any other direction to go to reduce the value. Okay, are there any questions to this idea, general idea of this gradient descent? Like the idea of starting from some random point and then going to some next point such that this point will reduce the value of the function. Just continue doing this until we stop and we cannot move.
Just a question about f. So, and the connection to deep learning. So f would be the loss function, right? Is that correct?
Yes, it will be the loss function. So if we have a model, neural net model, which, let's say we are talking about classification problems. So given some inputs, it will give at the end 0 or 1. Right? For each input, it gives 0 or 1. So now our f would be the loss from whatever labels neural nets assigns with respect to the ground truth.
Okay.
So we are talking about supervised learning. So we have ground truth labels. So we are writing a huge function which has n components, where n is the number of labeled samples we have in training data. So it's a huge function. And usually this function is not convex, it's not differentiable, it's not Lipschitz, it's not all these properties we want in order to guarantee mathematically the quality of the solution. But in practice, even though we don't have any of these assumptions, and we do run algorithm that proceeds in steps, usually it gives good results. We cannot prove that this is the minimum, but empirically we see that these are good results.
Thanks.
Okay, so this is like in general the idea, right? It's very simple idea of, you know, starting from some point and then trying to improve your situation, going step by step towards the along the trajectory such that each step reduces the value. It's a very good idea. So let's see how to implement this idea. Yes, because what is actually the problem in this idea is how do we decide where to go? So I'm standing at some point x0. I'm in d dimensions. I have infinite number of directions to go. So how do I know where to go? and I want to go in the direction that for sure decreases the value of a function. And even more, I want to go, ideally, I want to go to the direction that will reduce the most of the value of the function, not just a little bit. The most possible decrease, I want to get it and to go there for sure. So for this, we need to define several notions, and the notion of differentiability and of differential. So first of all, I need to define what is partial derivative. So if we are looking at this definition in the first bullet, partial derivative, so we have a function, again, this is our function that maps the dimensional vectors to real numbers, and partial derivative of this function at point W, some point, doesn't matter, some fixed point W. So we can define partial derivative with respect to xi, where xi is the i's axis. Yes, if we are talking about functions that map the d-dimensional vectors, so we have d axes, right? Axis x1, axis x2, x3, up to xd. So we have d axes. Like in 3 dimensions, we have 3 axes. In 2 dimensions, 2, axis x and axis y. Here we have d axis. So we define partial derivative with respect to i's axis as this limit. So think about this limit as the following. So we are staying at point W because we're talking about partial derivative at W. So we are at point W. So let's measure the value of the function at W, f at W. And now let's take a tiny step of size t, some parameter t. So let's move from W, tiny step of size t, along the direction xi. It's some axis, so we can move along this axis xi. Yeah? So this is what is written in the first argument. F at the point W plus t times ei. This is just what is written here is that we have moved from point W, a step of size t, along the axis xi. And this is the new point we arrived at. So now let's measure the value of f at this point. And now let's make a difference. So this is actually what is written here in the enumerator is how much the value of f has changed when we moved from W at the steps of size t along i's axis. Okay, this is how much the value has changed. And now let's divide by the size step t. So now this is the rate of change, right? Is this clear? If we are doing a small step of size t along the direction I, whatever is the thing that is written in the limit, it just measures the rate of change we did while staying at point W.
So f is from RD to R.
Right.
Therefore, both the numerator and the numerators are just numbers, right? So
these are just numbers, yes.
Yeah.
So let's say at point W I had value 5, and then I moved a little bit along axis xi, and I got value 10. So there is a change, right? It's changed by 5 units.
Yeah.
And now I want to divide by the length of the step I did.
So
If
that's actually basic calculus because in the sense that it's just a derivative, right?
Exactly.
Of a single function,
Exactly.
a single variable function, t.
Exactly. If you want to compute this, you're just doing a derivative when every other coordinates are fixed, and the coordinate xi, you're looking at it as a variable, and then you just do a regular derivative math.
And ei is like in the direction of xi. So ei is the unit vector in the direction xi, right?
Exactly. Yes.
Got it.
Yes. So what is important to understand from this definition is that this is just a number, as I am told, and it indicates, it represents the rate of change in the values of function f when doing steps from W along the direction xi. Okay, and we have D basic. So these are kind of basic directions, right? The basic direction is the direction along the axis, and we have D different axes. So we can compute the rate of change of the function while moving along each one of these. And this is exactly what is gradient. So the gradient is the second bullet is just recording the partial derivatives along each one of these axes. So each one gives some number, rate of change. And then we have D numbers, and we put them together. And this is a vector of D dimensions. Okay, but each one says us what would be the rate of change if we would go along each one of these directions. And what was our goal is going a little bit back, is that if we consider some point W0 we are starting from, and we are looking at all directions we can go, and we can go infinite number of dimensions, right? We can go not only along the axis direction. There are many combinations of axes, and we can go at each one of these directions. And we want to choose one direction to go such that the value of the function will be decreased, and it will be decreased the most among all possible directions. So the claim exactly says us what would be this direction. And claim is the following. So if we are at the point W0, so compute gradient of your function. So assume first of all that the function is differentiable. Differentiable, it means at each point W, it has a finite gradient. Yeah, because not at each point. So when it doesn't exist, for example, when limit, because we are talking about limits here, right? Partial derivative is the limit. So not all, the limit doesn't always exist. Yes, but if limit always exists for each point, so the function is differentiable. So the claim says if the function is differentiable, so if you are staying at the point W0, so compute this gradient and you obtain a d-dimensional vector. And now the direction of the steepest ascent when you are at W0, this is exactly the direction of the gradient. So this vector points exactly to the direction, such that if we will move along this direction, so we will arrive at the steepest ascent of the function at W0. But for our algorithm, we will need to take the opposite direction, right? Because we needed the direction of steepest descent. So for our algorithm, we will compute this gradient, and we will move along minus this direction, the opposite direction. Okay?
Mm-hmm.
Okay. So now I want to prove that this vector gradient of the function at some point W0, this is exactly the direction such that if we move along it, so we get the fastest increase in the values of the function among all other possible directions. Okay, so let's take some direction V. Okay, so let's take V, be some d-dimensional vector, and this is our direction we are considering to walk from starting from W0. And let's assume that V is of norm 1 for the direction, and doesn't matter. Yes, because the direction of vector V and vector V normalized is the same direction. So we're assuming for the simplicity that the norm of this direction vector is 1. And let's consider how much function f changes if we are walking along this direction V. So we don't know, so I didn't tell you how to measure it, right? I just told you how to measure the change of rate if we are moving along one of the axes of the xi, x1, x2, xd. We have it exactly written in the gradient vector. But now I want to take any direction, not direction along the axis. And to compute how much the function, what's the change rate? What's the rate of change going along this direction? It's not so difficult, and actually it's very easy to show from these definitions before, that for any vector v, the rate of change will be just computing the linear combination of rate of changes while moving along each one of these direction, x1 up to xd, times the coordinate from the vector v, which is our direction vector. Okay, this is what is written here. If I want to move along direction v1, v2 up to vd, this is my vector. So the rate of change will be v1 times the contribution of the rate of change if I would go along the direction of x1 axis. The contribution of the walking along the direction of the second axis would be v2 times the contribution of its appropriate rate of change, and so on, and so on. Okay, was it clear?
Mm-hmm.
Because I don't have, like for any vector change of rate, I have a change of rate while moving along each one of these axes. And to combine rate of change for any vector is just a linear combination of each one of these axes. It's very intuitive. And when we write it like this, so we see that this is actually, what is written here is actually the inner product between the direction vector v and the gradient of the function at the point w0. And when we write it like this, so we can use the formula of the inner product. And the formula says that the inner product between two vectors equals to the norm of the first vector times the norm of the second vector times cosine of the angle between these two vectors. This is what is written here. And then recall that we have chosen, we normalize the vector v, so its norm is 1. And now we are left with the norm of the gradient of the function times cosine of alpha. And what we want to say is, we want to say that when, for which directions v, this value is the largest, right? This is what we were looking for. We were looking at the direction v, vector v, that gives us the fastest ascent, yes, the steepest ascent, the largest value. So when this becomes maximized, so if we recall that cosine of any angle is from -1 to 1, and the norm of any vector is positive because it just measures the length of a vector. So we see that this quantity is maximized when cosine equals 1. And this is exactly happens when the angle equals 0. And this means, what is this angle? This is the angle between direction vector v and the gradient. So it means that this quantity is maximized when the gradient and directional vector are collided, meaning they point to the same direction. And this is what we wanted to prove. So what we showed is that we know how to compute for a differentiable function starting at some point w0. We know how to choose and how to compute efficiently the direction of the steepest ascent of the values of the function starting from the w0. And as we told before, taking the negative direction will exactly give us the direction of the steepest descent. Yes, the direction, if we walk at this direction, will decrease the values of the function the fastest decrease. And yeah, so this is the mathematical formulation of how to compute this direction, where to go. So I just will give the description of the gradient descent algorithm, and the next time I will cover some more. I will cover the guarantees that we can gain from this algorithm. So the algorithm, as we told, we start from some point x0. I don't know how we computed it. In real-time situations, this x0 is usually not just randomly guessed. It's somehow smartly guessed, okay, depending on the properties we know about, depending on the assumptions on the function f, we know somehow from prior knowledge. So yeah.
I just wanted to mention that the multiplication you see here between the direction vector v and the gradient is exactly, it's a scalar multiplication, and it's exactly the multiplication we talked about last time when we talked about projection. It's an example or an instance of that. Yes, so everyone can note that and make the connection. Yeah. Okay.
Yeah. So here I'm talking about regular, well-known inner product, coordinate by coordinate. Nothing fancy or nothing general. Very specific instance of inner product. Yeah.
Yeah. Exactly.
Yes. Thanks. So yeah, so the gradient descent, we are starting from x0, starting.
So now we're looking at in the slide, we're looking at the top right.
Yes,
Okay.
algorithm gradient descent.
Mm-hmm.
So we start from some x0 starting point. As I told, we don't know. It's not clear from where to start. Yes, the most naive case is start from randomly choose a point and start from there. But in real in real life situations, we know how to smartly guess this x0, depending on our prior knowledge about the function. But we are starting from any point, doesn't matter. And then we are making small steps of size eta from x0 in the direction of the steepest descent, which is exactly which we have shown in the previous claim, is exactly the negative of the gradient of the point x0. So our new point from x, starting as the x1 point, the point we will move to, is given by the current point x0 minus some step size times the gradient at x0. So this guarantees we are moving in the direction that will necessarily decrease the value of the function. Okay, so at the position x1, f of x1 is smaller than f at x0, and the change in this and the rate of change is the fastest. This is from the claim. So we are out at the point x1. Let's do one more step. So we can continue. So we're computing the gradient at the x1, taking minus, taking some side step. We don't know how large this step should be, but this is some parameter. Meanwhile, later we can define it somehow. And we are moving to the negative direction. So from the point x1 minus this thing. And we are at the point x2. Let's measure the f at x2. F at x2 should be smaller than f at x1, and so on until we are not improving anymore. So, or until we decide to stop. So after t steps, we can stop and we can return either the last point we arrived at, or in many real-life situations, usually people report the average of all the trajectory points, of all the points we have jumped through. Somehow it gives a little bit better results. So this is the point we report, x hat, and what we want to show and what is guaranteed by this algorithm, that if f is differentiable and it satisfies two more properties, which I will discuss in the next time, which is being convex and being Lipschitz, if these assumptions hold, we are guaranteed that x hat is if we are taking enough steps t, we will arrive at x hat, which is epsilon close to the true minimum. And even more, we can even describe how many steps we need to take to reach this. And I will talk about it next time, because I need to give more definitions and it will not just fit in this talk. Yeah, I decided to split it.
Good. How do you? So I guess the average has to do with stability, is it?
Yes.
What?
One of the ideas why, yes, of points why to take average. Yes. Also for stability. Yes, for stability mostly.
Any intuition you can give on this parameter here? Like you have the gradient times something. Any intuition on that number?
Yeah, so if you look at, it's a bit complicated here. So it depends on the number of steps we are doing, and it depends on some properties of this function f. It depends on the maximum rate of change f can have at any point going at any direction. So if this value is bounded, so it influences this parameter eta. Yeah. So so we'll talk about this. Okay. So maybe I will. Okay. Maybe I will talk a little bit about this parameter. So next time we can just focus on convexity. So yeah. So what does it mean that? So what does it mean that assuming some two more properties on f, what does it mean that the algorithm will converge? So it means that if we denote x star the true minimum point, yes, and we assume that there is one minimum point, global minimum point of the function f, and we are aiming to get there at x star. So the theorem, so there is a theorem to prove, I'm not proving it, I'm just writing it here. But there is a theorem that shows that if we're making t steps, and t is given here in the formula, it's some r square times rho square divided by epsilon square. So if we're making this number of steps and we define eta to be as written here, right, square root of this number of this parameter here, which depends on t, the number of steps, and depends on rho. So if we set these parameters like this, and epsilon is the approximation quality we are interested in, right? So this is the value of the function at the minimum point, and the value of the function at the point the algorithm found. Yes, so we want these values to be close up to epsilon, very, very close. Yes, so for us, it would be satisfactory, and for us, it will be enough to say that x hat is very close to x star. So we will report, okay, we found a minimum point. So what is this number of steps? So it, of course, depends on the quality we are willing to reach. And it also depends on this parameter rho, which I told, which is the bound of on the rate of change of the function at the global. Like, doesn't matter from where we start, doesn't matter where we are looking at. If the function behaves in a way that the rate of change is bounded, meaning there is no any place in the space and no any direction such that the function grows like crazy in unbounded way, meaning the function has a somehow bounded growth rate of change at every location. It's nicely behaved. It's not going crazy at any place. So so this parameter influences the number of steps we need to do. Okay, the crazy is the function, you see, so we say the function is crazy. It means that at some place you can do a small step, and then the values have been increased drastically. Yeah. So if the function decreases the function, the larger the number of steps you need to take, right? Because it appears at the r squared times rho squared. The larger this rho parameter, the larger the number of steps you need to do. So if the function is kind of nicely behaved, the number of steps is not so large. And then this eta is not so large. It should be kind of small.
I see.
Sorry, and what is r squared?
Okay, yeah, and r is kind of an assumption we are making about the location of this optimum point. Okay, so we parameterize it. It's not an assumption. It's actually a parameterization of the location of this x square. So if the norm of x hat, yes, this is, sorry, x star, this is the optimum point. So if its norm is bounded by r, so so it also influences the number of steps we need to do. The further it's from the 0 point, from the center of the axis, so the larger the number of points we need to do. It's some mathematical, it's really mathematical assumptions. It actually doesn't play a huge role here. The biggest
So it's like the optimal is within a compact set, or a bounded set, which is a ball around 0, basically.
Yes.
Yeah.
Which we always can. It's we always look at this. So in many cases, it's some constant number. It's nothing that really impacts here much, even though it appears here in every place. Yeah, but okay, but it's in theory, right? So yeah, in theory we know this is number of steps, but in practice people don't really do this. They don't really compute. Okay, let's compute how many steps we need, and let's compute eta, and then see the things matching here, and we have here a miracle solution. In practice, and does it work? In practice, people just do some search on the size of eta. Okay, so they try some, they start from large numbers of eta, and they see that when they go along the trajectory of the points they obtain, they see that the value of the function is not stabilizing. It starts to decrease and then it increases. So we have jumped too far. We wanted at each step to decrease the value, but then few first steps it indeed decreased, but then it started to increase. So we jumped out from the trajectory of the minimization. So it was too big step. So let's try to reduce it. So reduce it by half. So kind of, you know, this binary search.
Binary search, okay.
And then see that you are along the direction where you can increase, but not that much. Like every fifth or sixth step, you see that you decrease in overall. So you continue doing these small steps and you decrease. In general, the smallest theta, so if theta is small enough, so for sure you will at each step only decrease. But the thing is that you don't want to take eta too small, because you will not converge in a reasonable time, right? You can do small steps and walk forever. So you want to do from one side, you want to do them big enough, and from the other side, you want to do them small enough so you are not jumping off the minimization trajectory. So it's
it's essentially an empirical parameter that you search for.
Yes, in real life problems, yes. But in this math environment, you're not searching for this parameter. It's given here, described by the other parameters that depend on the properties of the function.
Which you'll explain next time.
Yes, I hope so.
Yes, great.
Yeah.
Okay, any other questions or comments?
So we are doing this iterative updates because finding the first derivative and setting that to 0, that will not get us to the minimum.
Because, okay, yes, it maybe will get, depends on the properties. If f is very, very nice, it will give you. But the thing is that it's in many cases, it's very difficult to solve this equation. If you do derivative and set to 0, now you need to find the values that bring it to 0. And, you know, if it's a polynomial of 10th degree or 20th degree, there are no any formulas that can solve it. So these equations, they are true. And if one solves them, it gives the right solution. But in most cases, it's just not possible to solve it. Or you solve it iteratively by doing this algorithm descent.
Okay.
Yeah. Right. Like in 3D or in 2D case, or in one variable, yes, like functions, as we know, like y equals x to the power of 3 plus 20x or something like this. So yes, if we want to find minimum point, this is what we are doing. We are doing derivative equals to 0. In some cases, we get nice equations that we can solve using some analytical tools, some formulas. Yeah, but when we are doing this for functions from d dimensions, it's we don't have any tools to solve such equations.
Right. Okay.
Yeah. Thanks.
Yeah, this will also even become clearer when we talk about backpropagation and the loss function.
Yeah, this is just a snapshot from the field of optimization, the most purest mathematical representation of one of the optimizations algorithms. Purest meaning make a lots of assumptions, unrealistic in real life. And under these assumptions, the algorithm will give you whatever you're looking for in a pretty fast way. Yeah.
Great.
But this is the base for all the rest algorithms. Just people do variations on this. Heuristical variations of these basic methods. They just can't prove anything, but in practice it gives solutions, good solutions. So it's worth understanding it, you know, the heart of all these optimization algorithms.
Yeah, very important point. If you understand the background and the theory, it's easier to see how the heuristics are later applied and what is missing, what we don't know. Like we can't solve that when the gradient is equal to 0 and things like that. More questions or comments? Okay, so thank you very much, Ora, and we'll continue next time with your things here about the convexity and and how you get these estimates of how many steps we need to make. Okay. Thanks.
Yeah, thanks.
Bye-bye.
Bye.
Thank you.